Well, do you want to get started? I want to be respectful of your time, Sylvia. Um, you can go ahead and introduce Springbok, and go ahead and roll into your presentation. I think, as per normal with these meetings, if you have a question, you can interrupt the presentation and ask your question, and we can talk about it. Sylvia and the whole gang is here to answer all the questions, so thank you all for being here. Appreciate you very much. I appreciate, we were just talking about the Australian study. Ian Woodcock's in Australia has a bunch of MRIs from pediatrics that they're gonna upload into Springbok, and they're gonna work their magic on it, and we're gonna publish on it, and it's gonna be, I think, a really, really good thing for early onset in pediatrics. So thank you so much, um, Springbok, for everything that you're doing for the FSHD community, and thank you so much for being with us this evening. So I'll turn it over to you, Sylvia.
Thanks. Yeah. As Ali said, please do feel free to raise your hand. Oopsies. Raise your hand. It's hard for me to tell if somebody is doing that. So Ali, if you need, feel free to like interrupt me if there's some sort of like hand raised or you know what I mean? Like if I'm
Yeah,
just
I can do
like
that.
all in my own world. But once I start talking about muscle and FSHD, I kind of get in a zone. So it's something that I'm passionate about and excited to chat about. So yeah, my name is Silvia Blemker. I am a Chief Science Officer and co-founder of Springbok Analytics. Springbok has been around a little while. It actually came out of the University of Virginia, where I'm also a professor of biomedical engineering. So I've spent my career learning about skeletal muscle, trying to better understand it and better understand how disease impacts it, and also in doing that, developing new ways to study muscle, quantify it, and in order for us to learn more about it, in particular in patients. Today, there's a number of folks from our team here. Uh, we've got David Lane, who is our director of business development in Australia. This time worked out well for him. We got Scott McGargy, who's our CEO, and then Emily McCain is our director of R&D here. And then actually Morgan Dahlman is here. She is a postdoc in my lab at the University of Virginia who's also interested actually specifically in understanding pediatric FSHD. So just thought I would shout out to them. So a bunch of muscle nerds on the call. So I wanted to say, so we've been working with Ian Woodcock for a little while, and we actually have processed some pediatric FSHD data. It's a very limited data set that he had collected a little while ago. We call it a retrospective analysis because he'd already collected the data and essentially was sitting there. And so we worked with him. So what everything that we've learned about pediatric FSHD is from a sort of analysis of that data. So I thought I would just talk about that data. So I actually do have a lot of graphs, but I know this community is really astute and has learned a lot about the disease. So I'm not going to try to like gloss over anything. I just figured I'd spend some time showing you what we've been learning about uniqueness of FSHD in kids. Just a little bit about kind of our overall vision. We're really excited to use MRI in a way that's not usually used. So usually, if a patient goes to get an MRI, it's usually to look at a certain region of their body to figure out, if they've gotten an injury or what have you. Well, we realize that there's tons of information that you can get from an MRI that's kind of outside of the norm. So that's what's led us to develop this technology that goes from a very rapid whole body MRI scan where we can quantify all the bones and the muscles of the whole body in a way that can really give new insights into the functional capacity of the body and the status of the muscle health in that person. We're up to 140 individual muscles across the body and counting, always trying to add new ones. in particular in FSHD, ones that we're ultimately thinking of adding would be particular in the face, potentially in the neck, in the hand and the feet. But so we're always adding, and also in the pelvic floor. But we're up at 140 right now. So we also do actually have more things that we can quantify from MRI, but today I'm going to talk mostly about muscles, since that's the really focus here. So just a little bit. Our original paper that described how we do this in the lower extremities and the legs, sort of belly down, was published over 10 years ago. So that's how long we've been working on this. And actually, one of the first applications of the technology was in children with cerebral palsy. So we had originally thought about children from the get-go when we started working on this technology. So that's why, one of the things we really focus on is making sure that the imaging protocols, so the part of the MRI, so it is based on an MRI scan, but the way in which we collect the MRI scan is as easy and seamless as possible and fast, so that it is amenable to a child. And then we just finished our full body kind of research paper that describes all of these muscles and our kind of reference databases or databases. Um, so that's just coming out. So, okay, to FSHD. We've been really interested in this, this quandary in the field about how heterogeneous FSHD is obviously across the kind of arc of progression, but then even at a similar potential state of progression, different muscles are affected in different people. And so that's where the MRI can really give us insight, is which muscles are affected in a particular person, even just looking visually. So what we're looking at here, the visual, are essentially, we call them digital twins or models of individual patients, where we've taken their MRI scan, identified each muscle within the MRI scan, and developed and created a three-dimensional computer model of their muscles. So those are actually the shapes of all of the muscles in the body of specific patients with FSHD. And so we have that 3D reconstruction, we call it. And then within each of those, we can also quantify how much fat has infiltrated within the muscle, which is thought to be one of the kind of most the best biomarkers of disease progression in patients with FSHD. So as muscles are expressing DUX4, that leads to, obviously, is a toxic to the muscle and leads to damage in the muscle and ultimately progression. And as the muscles progress, the muscle tissue is replaced by fat. So that percentage of fat is this marker from 0 or very low would be a muscle that's quite healthy, that has no progression, all the way to very high, which could be upwards of 80 to 90% fat, would be a muscle that's very progressed. So we've actually color coded each of these muscle models based on the amount of fat that's inside that muscle. And so what we see is pretty good heterogeneity, across people in terms of severity. Some cases you see right and left differences. For example, this case in their thigh muscles on the right side, very affected. On the left side, not as much. In other cases, it's more symmetric, right and left. Certain muscles are affected early in some people. This is an example of that. This muscle in the thigh, it's called the rectus femoris. It's very affected, versus in other cases, it's not affected. So just illustrating this profound heterogeneity. So, and the other thing that we found that's really exciting is that we can do a better job of really understanding the impact of the disease on the whole body. And so, because we're really measuring every single, or many of the muscles, not every single muscle, but most of them. So I wanted to show some insight that we've gained from that. So we're going to look here. First, I'm going to start with adults with FSHD because we do have actually a fair amount of data. We've actually started what we call a data lake, which is a collaboration with a number of researchers in the FSHD field, including Seth Friedman, who's at Seattle Children's Hospital, also Doris Long, who's at Kennedy Krieger, and then also the Jeff Statland and the entire kind of Move Plus and Wellstone organization. So we've been collecting or bringing together these MRI data from a lot of different data sets to give us really a better understanding the disease. So what I'm going to show here is kind of a slice of that, of the subset of the patients that have been participating in the Move Plus study, which is a natural history study in patients with FSHD, so that we can better understand it. And so so what I'm going to show here, so the other thing that we all know, if you look up FSHD on Google or Wikipedia, you usually end up with a visual like this that we see up here, where FSHD is usually impacting a certain set of muscles in the shoulder girdle, the upper arm, and then the tibialis anterior. This is what's shown. So, while it's kind of it goes actually with the name of the disease primarily, the question is, how representative is that really? So let's look at adult patients. So first I'm going to highlight, so each of the kind of columns here in this plot is a muscle. Each of these dots is a person's muscle. So most people, if their data was complete, would have two dots. So one dot for each side, a right latissimus dorsi and a left latissimus dorsi. And then the y-axis is this fat fraction that I was talking about. So 100% would be very progressed, 0 would be very healthy, and then everything in between. So and so each of these dots are a person, and so we can see these are the particular muscles that are highlighted in this diagram. So indeed, we see a fair number of patients that have high levels in those particular muscles, where the dots that are up here closer to 100%, those are very progressed. But we also see people that have muscle dots that are actually not super progressed in those particular muscles. The other thing I'll note is the upper body muscles are color-coded in green, and then the lower body muscles are color-coded in purple. So we can kind of see, the sort of distribution of upper versus lower. Some people think that it's more involvement in upper extremities. The name kind of implies that. So, okay, so those are the muscles that are in the diagram. So let's look at the rest of the muscles, because obviously we have way more muscles. Well, my answer to that question is no, because if we look at all these other muscles that are not on the diagram, we see that some of them, oops, there's actually, if we look over here, where did that muscle? I lost a muscle. There we go. Well, I'll show you this. This is like the full image. We see that there's involvement across all these muscles. Very few muscles are actually spared over here, but there's involvement across a whole range and many muscles that are not included in this diagram. So this is one thing that we think it's important to really kind of make clear, is that FSHD really is a profound whole body disease, and I feel it's a little silly for me telling patients or parents, because you already know that, but I do think it's valuable for us to really show that to the whole community, because I hear stories of patients who perhaps uh, their their doctor isn't as familiar with FSHD and in the community, so maybe they just see what they read and they don't really understand why you have the profound impact of the disease when they see these types of diagrams. So I think we're hoping to kind of change the dogma a little bit and really illustrate.
Sylvia, I
So
have a question real quick while we're on this about the whole body involvement. How do you guys have any interaction with regulatory like FDA or in the EU to kind of show them this, that this is more of a whole body, like you said, um, profound involvement so they understand the urgency of getting a treatment out?
Yeah, we you know, the we have we the first thing I'll mention is that Lucienne Rocco from FSHD Society organized a panel of scientists to speak directly to the FDA, to talk about this specifically, and for a couple of things, really kind of to inform them more about FSHD, but then also about the various ways that we can now measure the impact of the disease and then impact of treatment. And so this is something that we talked about in those sessions that I think, and they actually were really receptive and kind of appreciative of this type of information. So absolutely, I think that is an important piece of it so that they can understand this impact. So yeah, something we're working on, and we continue. We're also really working on, in general, having FDA see these MRI measures as a metric of disease progression. That because the challenge is, like, over a short period of time, the changes may be only localized to one or a few subset of muscles, where you wouldn't it's really hard to see the global impact on function, but the progression is there. And so that's where one thing that we've been trying to highlight with the FDA is the value of looking at the muscle level in the MRI.
Thank you. And I have one more follow-up question to that. So I'm not a muscle nerd, so I don't know what all these muscles are, but the muscles that impact the diaphragm or the lung restrictive, is there a way like to highlight that to say, because we as patients and parents know that restrictive lung disease is pretty prevalent in FSHD, and can you correlate like these muscle weaknesses in the core or whatever muscles make the diaphragm or the walls expand so that you can take a big breath. You can correlate that directly to something like respiratory, which leads directly to early death.
Absolutely. Yeah, that we right now don't have the diaphragm or necessarily like primary breathing muscles. But it's actually something that we're really interested in. We have a few researchers that we're working with who are aiming to develop and kind of work with us to develop a way to image not only the structure of those muscles, but actually you can measure the function of the diaphragm with MRI too. You can measure how it's moving during breathing, which I think is can be quite insightful. So yes, that's something that we are super interested in developing right now. So yeah.
Okay, thank you.
Um, Okay. So back to the kind of the focus of this presentation. Now that we kind of highlighted the involvement in adult patients, then the question is, how does this look in pediatric patients? Where one muscle that I'm going to point out, which is interesting, is this muscle over here that unfortunately was like blocked off in my prior slide. The semimembranosus, or as David Lane would say, the semimem. All the Australians like to shorten names, so I'm going to call it semimem. It's one of the hamstring muscles, so behind the leg, and it is in adult patients. If you're going to find one muscle impacted, it's that muscle, because I've ordered these by the average fat fraction across all the patients in this cohort. So this one, almost all, if not or most of the muscles are highly affected. So that's kind of an interesting scientific question, is what leads to that? Why is it that muscle? And all those things. And those are types of research questions that we're interested in. But let's kind of keep that in mind. And so let's compare that with these are pediatric patients now. These are from Ian Woodcock's original data. So he's got some new data that, or a follow-on data set that we're now working with him on, that's a little bit more inclusive of muscles. But this is the group that we have from him. So the first thing so I pointed out the semimembranosus here on the right, that hamstring muscle behind the leg. Well, we look at here at the order here, and that muscle is only, you kind of have to scroll over to find that one over here. So even just looking at one particular example muscle, we see that the kind of stark difference in the adult group versus the pediatric group. The interesting thing about the semimembranosus is it doesn't matter like which, all of the cohorts that we've studied in adults, it's always that muscle that's first. But here we see in the pediatric patients, that's absolutely not the case. But then, then you can start looking across the muscles. We do see a little bit more. So I've kind of highlighted the upper versus the lower, a little bit more involved. Kind of the upper extremity muscles do tend to be a little higher in these pediatric patients overall. And but then, we do see some of these other kind of lower extremity muscles, but are not necessarily the ones that are highest here on the adults. The other muscle I wanted to turn our attention to, and I always can't find it, is the tibialis anterior. I should have put a line over it or an arrow, because where did it go? Tibialis anterior. Where is it? Where is it? Where is it?
It's to the right more.
Why
Keep
can't
going.
there?
Keep going. A few more to the right.
Oh, here it is. Yeah, there he is. Okay, there it is, right there. Ooh, I could draw. Here we go. I'm gonna draw a little bit. There we go. See if this actually works. I feel like I need like a thicker line. There we go. There we go. There is a tibialis anterior. But let's find that muscle up here. I feel like it's not all the way to the left. Do you guys see it up here?
Yeah, it's about the fourth one from the left, or maybe fifth.
Yeah, over here. Yeah. So, obviously different kind of impact of an involvement, but interestingly, in adult patients, that's probably the most studied muscle in adult patients with FSHD. Most biopsied muscle, most looked at in terms of strength, of impact, so we know the most about that muscle. And, part of that is because it does progress, it impacts, uh, you know, mobility due to the impact on foot drop. But I think it's important to realize in these kids, it's not the same type of thing. So if you're going to choose a muscle in kids to really kind of hone in on it, probably doesn't make sense to choose this muscle. You'd probably want, and not to say that doing biopsies in kids is as amenable, but just in terms of now translating all the knowledge that we have about like DUX4 expression and how that relates to things like fat fraction, things like inflammation and other aspects. A lot of that information that we have in adults is in the tibialis anterior, but it's unclear how much that's really going to, translate up to the kids, given especially this muscle is not very involved.
So, Silva, here's $1 million question. If DUX4 goes out and randomly or whatever seems to attack certain muscles with FSHD, why would it attack different muscles if it started earlier than if it started later? Does anybody have a hypothesis on that? Like if it's later onset, it goes after this muscle, but earlier onset, it goes after this. Like what would, is there, why?
I do not have an answer to that question. Uh, I've similarly, that is the $1 million question. I think that, one thing I'll talk more about in a minute is the impact of growth. I do think that is something that in the pediatric population is an added like kind of like factor, or I don't know if it's wrench in the system, but something that's also impacting what's going on in muscles profoundly. So I have to wonder if that may lead to some of these differences in where and how DUX4 is expressed in muscles because of that influence of growth and the hormones and all these things.
Wally, you made this, Dave. You made an interesting comment when you said where when it started, because it started for everybody at birth or at conception or whenever, right? In fact,
Right.
it's when it manifested.
Right,
Yeah,
you're right, Dave.
yeah,
Right.
absolutely.
So is there a difference based on when it manifests?
Right. Well, I guess,
Because it's always there.
yeah.
Right, that's what I was trying to say. Like, why, if it manifests later, does it go after a certain muscle? If it manifests earlier, it goes after a different muscle. But you're right, Dave.
Yeah,
Thanks.
yeah.
Well, actually, could I just mention one thing too is I guess I'm not totally sure that I'm not sure how to explain this, but if you took all those pediatric cases that you see on the top and you give them another 10 years, isn't it possible that they might look like the bottom? So it's not like all of these people were the MRIs were taking right at the onset of their symptoms, right? So it could be some of these adults did have um, significant symptoms when they're younger, but now they're 10 years older, and so just eventually different muscles are affected more. I don't know if that makes sense, but
Yeah,
um,
no, it's a good point. That's what makes all of this so tricky is that this is time and person variable. So it's hard to match cohorts like that too. Um, I guess maybe I'll say that even in a like some of these extremes like are that's why I kind of point out the extremes. So like in a patient that's very early on in their you know since kind of diagnosis or onset would have this muscle would be high already. That would be one of the earliest ones in that case, which I think is important to see that like that muscle is all the way over here. So in this case, if that makes sense. So if you were like scale this back and you chose the adult patients that may have like kind of average muscle involvement, if whatever that means, I think it would still look different, I guess is my point.
I was just thinking that too, if you look at the lower one, those I don't know, maybe the black dot is the mean. I'm not sure exactly what it is, but um all of in general it seems like the lower ones are higher. So it it just kind of shows that a lot overall kids don't quite have as much fat infiltrate, but as you keep getting older, it increases with all of the muscle. So it just, I guess what I was thinking is, maybe on average, the latissimus dorsi is more affected when you're around 10, but then once you get up to over 30, then the semimembranosus, who knows why ducks attacks those muscles. But to me, time just seems like a big component of this. And not that there's a big difference between children and adults, but maybe curious to know what you think of that.
Yeah. Yeah, I guess once I guess it's important to realize that like they don't go back down. So once a muscle's up here, it won't go back down.
Right. That's what I was thinking is, the latissimus dorsi goes up to a certain, well, I guess I was just trying to compare.
Yeah, this one that one I would say is more similarly impacted since they're both kind of on the right here.
Oh, right. Yeah.
Yeah, I think where the stark differences would be like between cases like that are like on the left here versus on the right
hmm
here. That's where I think it's kind of more of a dramatic difference.
Yeah. So that just makes me think that overall, the anterior tib gets often more affected in, 20s, 30s, 40s. Just it takes longer for ducks to get to that muscle for some reason. Not that it's anything to do with when the symptoms first develop.
Right, but the all like a very low affected adult would have higher fat fraction in the TA. So it gets more infiltrated with fat earlier from diagnosis than TA. Like if I
Okay.
were to show you somebody with minimal like involvement, they would have higher TA, if that makes sense.
Okay. I might have to think about that more, but thank you.
Yeah, yeah. No, it's complicated. But actually, let me just move to the next slide because it actually kind of speaks to these questions. If I can actually click. Oh, I think I have to stop doing this thing. Okay, so they're not the same. So, oh, I need to clear now. Let's just erase my little thingies. Okay, but thanks for that discussion. That was good. Sorry, what's, oh, okay. Okay, so the next thing I wanted to talk about is progression. We were talking just about that. And so again, these patients aren't the same kind of matched in terms of like quote involvement, which is tricky to do, but I think it's still meaningful to compare and see what types of trends. So the one thing I'll point out is that on average, all the muscles increase in fat fraction in adult patients with FSHD. Sometimes they actually go down, and we can talk a little bit about why that would happen in adult. Generally, it's, I think, a somewhat a muscle that maybe is compensating, and a certain region of the muscle may actually hypertrophy, and so that leads to like the fat fraction going down a little bit. But overall, we're going to see progression across, and somewhere on average between like 0.5% up to like maybe for some of them actually is almost like 3 or 4%. But let's see how that compares to the same group of patients. And these are both 1-year follow-ups. So these are both over the span of a year. So these are the pediatric patients on the top. Again, one over the course of 1 year. And these are on the same scale. Oh, I forgot to mention the y-axis now is change in fat fraction from the baseline. So what's changing in each muscle? And so even by looking at the range across, like we see, the range here is plus or minus 20%. So we see, lots more dots up and down in the pediatric patients than we do in the adult patients, even whether it's up or down. But the thing that's really compelling or kind of confusing, I would say, is the down, right? That there's a lot of muscles that are going down. So what is that? Is it that patients are getting better, or what's going on? So that's one big question, but we also see a lot more increase as well. So definitely the kind of speed of progression, which we all know this does differ in the patients. So I wanted to talk about a little bit why, like because this actually, I think, will make trials in pediatrics more difficult, because while the biomarker fat fraction in adult patients has been sort of shown as a good representation of what's going on in the muscle, in the pediatric, this is a bit confusing, that you have a biomarker that of progression where we know there's progression in the child, but it's actually going down. So the other thing I'll say is, to really understand this, is we need more, more of a data lake, because that's a pretty limited data lake, and it's relatively early, lower affected kids in the specific cohort that we were looking at with Ian, and we were just talking about the limitations of that. So there is this Move Plus Peds study that's coming online, and so whether or not you've heard of it, this is an extension of Move Plus, so the data that I was just showing you in adults, but now it's applied to patient or to children, where there is an MRI. It's a natural history study in pediatric, and so we urgently need that data to now really better understand what are the real differences, because we just talked through the data set from the patients or the kids is relatively narrow, and we really need to better understand this. So and this is for those, I think probably the FSHD parent community could help refer people to the study, but if you're interested, or if you've heard of it, definitely a plug to be involved. But I wanted to go back to this question because I think it's an important one. So what's going on? Now I'm going to talk a little, I'm going to like zoom in on like one of the muscles, and I just chose pectoralis major because it's got this big range. Some muscles are progressing a lot and some muscles are actually going down. So what's really going on? So let's look at one kid with FSH. So I'm gonna just like go into one particular case to kind of tease apart what's happening. So what we're looking at here is 2 time points. And so each dot, so the first dot is the first time point and the second is the second. And we're plotting the change in the volume. So now we're not doing fat fraction. We're actually just doing like size or volume. So the red is the total size of the muscle, the total volume. And then the blue is how much of that is actually fat, so in volume. And then the difference between these would be lean volume. So, and we're plotting the change. So what I've done on the x-axis here, instead of time, I put height. So essentially the child is growing. It's grown upwards of, a little more than 6 centimeters. So a decent amount of growth, I would say, over a year's time. So it's natural. Children grow and their muscles grow with them. But there is a little bit of progression of fat volume too, right? So this is really the challenge here. But even though there's progression of fat, then you will see in this case, because of also the kind of confounding growth, you're going to see a decrease in fat fraction just because of the nature of the muscle is getting bigger from growth. And there's, so even despite the increase in fat, potentially by some downstream effect of DUX4 activity. So that's really the challenge. So now our fat fraction number is going down. So how do we interpret that? How should we be? And the big question then is, well, okay, it comes down to the lean volume increased, but did the lean volume increase as much as it should have? Like how much should have the muscle grown relative to their age and their size and all these things and the progression of their body? That's really the challenge. And so we see here, like what I plotted here now is like that change in the lean volume versus the change in the fat fraction in several of these kids. So we see it's negative correlated. So as up here on the left, this would be somebody whose muscle's getting bigger. And so their fat fraction is going down. And then some of the kids are actually, the muscle is getting smaller and their fat fraction is going up. So this would be the case that would be more like what you would see in adult patients, but we see a fair number of kids that are up here. And these are really the ones that are in these big growth spurts where that now their growth is sort of going to confound their fat fraction. So unfortunately, right now, I will say that we have a fair amount of knowledge of like their trajectories of muscles in adults and even into aging population. At Springbok, we're able to adjust the fact that as you age, you actually have a natural decline in muscle. It's not as profound as what happens in growth, but you have a slight decline and we can account for that. But in the children, we don't have similar reference curves in terms of how much muscle and lean volume should be increasing relative to sizes. So that's something that we're really trying to figure out how to get to, because I think that's really going to be needed for us to really understand what's happening in these muscles. So we've been trying to work with a number of different foundations, maybe to raise funds to try to get a typical developing study going so that we can match with ages and having girls and boys and be able to really understand what the natural progression of these muscles are versus age.
Is there any correlation with this with the assumption as to whether a drug developed for adults would be applicable to pediatrics?
In terms of like the impact of growth?
In terms of looking and saying, what I'm seeing is saying, well, the effect on muscles is different because it's different muscles, and as you grow, all of the things you've just been showing us.
Mm-hmm. Yeah, no, I think it is, and it all kind of comes down to like the mechanism of action of the drug. Some of them are really getting at the gene therapies are really getting at modifying the within the cell in terms of convincing the cell essentially that it shouldn't be producing DUX4 anymore, versus others are trying, like myostatin inhibitors, that are trying to modulate the kind of decline, like essentially promote muscle growth. So I would say that those different mechanisms, I think, would have different impacts on or different differences on the like pediatric application. So yeah, no, I think it's a consider. I don't have a good answer, but I do think it's a really good point. And that's also what I think doing these, like the Move Peds, will help better understand also, is like what is the course and how is that affected. It may or may not be different in these kids.
Will the study that Ian's doing right now with the 50 scans, will that go into the data lake?
Yeah, yeah. The only thing is it's not quite the coverage that uh that the Move Pleats is getting. So I think that's one. But indeed, yes, that will go into the data lake.
And I had one more question. You touched on a little bit about compensatory muscles. I think just again, anecdotally, with my son growing up, kids
Hmm.
compensate. I mean, they just do it because, it's just they're growing up and their muscles are getting weaker right away. So they're like, they have all these compensations early and they don't
Hmm.
even really realize that they're compensating because that's just how they have to move. And you
Right.
said something about compensatory muscles merging with the other ones or maybe getting stronger around it, and that would that make the growth go down or make the fat fraction go down? Is that a possibility
Yeah.
with the, because I think the kids are really, they're really clever about the compensatory because they're just learning how to do everything.
Yeah, absolutely. Yeah, they're kind of they have a little bit more neural plasticity to adjust the way their brain is
Right.
in their muscles. Yes.
I was
So
just,
yeah.
oh, sorry.
Hmm.
I was just going to say when they're compensating though, they would use other muscles then, I think, right? So I'm just, you would be able to detect that on the MRI. So my daughter, for example, her serratus and rhomboids are really weak, so her levator is really overactive. So she has, these thick neck muscles. You would be able to tell the compensation from that, but I don't know. That's just what I'm thinking is would be the easiest thing to see when they compensate because those muscles will be stronger than typical
Absolutely.
would be.
Yeah, that's something we've been looking at. With the more data you can see it, like essentially if you look at like they're called synergistic groups, like you say, like some muscles, because each function in the body there's more than one muscle that can do it. We call it, like, we're a redundant system. Like we have three hamstring muscles that each do the same thing, cross the same joints and everything. So like as one would be progressing, and if the other one's still healthy, it can absolutely compensate. And so that's one thing you can see, like at the kind of if you look at the group level, you can start to see when that happens, and you definitely see that in for even in adult patients too. That's why you'll get those declines, but they're not quite as profound as the growth impact. But indeed, you can see that as well.
And I know that Ian and some of his kids, they had some non-ambulatory kids as well. In
Hmm.
this data, were some of them non-ambulatory, do you know?
I believe so. Yes. I didn't have like the clinical much other information other than just the MRI data for this. It's kind of like focusing just on that. But yes, I think there were infected. Um, yeah.
And I know Ian, I believe he's going to match like, the muscle fat infiltration and all the things and match it to the repeats, right? So it's kind of predictive, like if you have this repeat, this is, but what about function? Are you matching like if it's fat infiltrated, then this is how much function you should have?
Yeah, that's in move peds, for sure. That's what the kind of the goal is matching the muscle MRI with the function. I think the other piece of that is figuring out like what are the best functional measurements in the kids, because my guess is it's not gonna be the same as in adults. So I think that's the other piece, but yeah, no, that is the absolute goal of that.
And then, so that all kind of goes together for a predictive model that if you have this repeat, if you have this function, this is how your muscle looks, then could you say that 10 years down the road or 5 years down the road, you may not be able to lift your arm up to your head or walk? Are we that far yet?
Well, let's move on. Uh, so that's really our vision with integrating all of this data is to do a predictive model. So the idea is essentially creating we call it a digital twin, but a model of an individual patient that incorporates data, like you're saying, Allie, like molecular level data, things like D4, Z4 repeat length, methylation, then the muscle level data where we can incorporate the fat fraction. We have other kind of more detailed measures of things like distribution of fat in muscle and things like that that can go into it, then the functional clinical data, and then it also, for the patients, this growth information, I think will also be important, depending on their age, and even the status of their skeletal system. And then based on that, have a personalized prediction of progression that ultimately, like if you can imagine, that almost serves as a, you might want to call it like surrogate placebo, so that person has like a matched placebo person in a trial, so that you can compare how their progression would be different or similar to like what's predicted. And so we've actually been doing this in adult. So we've tested out this concept in the adult patients because we have much more data. So you obviously, for this type of modeling, you need a fair amount of data. So this is an example of a model that we did where we've incorporated a number of different parameters, things like a D4, Z4 repeat. We actually do this at the muscle level, sort of accounting for the fact that different muscles have different kind of progressions and a number of other parameters. And then we can incorporate those in the model and predict whether it's change in fat fraction or lean muscle volume. We can do both of those within the muscle. And so this is the data lake that I was mentioning that we have a number of different studies that have different time points. We have up to 118 muscles per patient in this cohort. This is all retrospective data that where we've captured in here. So over 100 unique patients, and so thousands of muscles analyzed into this data set. And so when you use this type of modeling, you sort of reserve, I'm not going into the details. We have kind of these different stages that represent different scales within the model, but essentially we use 80% of the data to train a model and then save the other 20% to test it out to see if whatever we fit with the model actually, how it does in the testing world, which is ultimately kind of where you'd want to be. So this is kind of a snapshot of what the model does. So in terms of predicting change in fat fraction and change in, so between the training and the testing. So we're seeing some predictive performance. So we can start to predict which muscles are going to change more. And the other thing that we get is like which of these parameters that went into the model are impacting. So the further out these dots go, the more impactful that parameter is on the outcome. So things like muscle, which muscle it is, that impacts it. The other thing is regional variation, D4, C4 repeat length. The other thing that I find really interesting is actually the size and properties of the bones also influence the progression, which there's kind of a lot of maybe we're not sure what's going on there, and maybe it's a surrogate representation for something else, but I do think that's useful. And even back to children with they're changing their bone a lot over time, like that's also something that could be really kind of important to think about. So then so we can then take, and I was kind of speaking to this to the group level. So essentially, if you have multiple muscles in a group, then we can group them together and see how the model does there. So, and because this is kind of moving towards function, and so this is looking at the fat fraction changes across a variety of groups, across the upper extremity and the lower extremity, and also lean volume change. So we have kind of two parallel models that do each of those. So showing the predicted versus the measured. And then finally, we have a model sort of back to the vision that you were saying, Allie. So ultimately, if we predict the group level change, then can we use that prediction to predict a change in function? And so that's what we're showing here. So this is showing how including these specific muscle groups, and these are the output of the group level change, in addition to the timed up and go at baseline, can predict the change in timed up and go over time, which I think is kind of like to the kind of broader vision. And the unfortunate thing is the data set, because we were kind of merging lots of different sources that have all different functional measurements, the amount of data we had for the function piece was less. So the other thing we're really advocating for is sort of agreeing on what the functional measurements should be. And so actually this paper is published, if anybody's curious about this modeling paper. So with that, I'll just kind of wrap it up in terms of like where we're going with this. We really need more data types. That's one thing that we're working on. But then in particular for pediatric, we just need more data. I think the more data we have, the more we learn about what's unique about these patients. And then also, as I mentioned, just having these typically developing children to kind of match and understand their growth.
How many do you need typically developing, do you think?
I think we've mapped it out to at least get a cross-sectional about 100 kids would give us a pretty good matching in terms of the age range, like from 5 to 16 is kind of what the pediatric Move Plus Peds is moving for. And so that would give us at least enough data, girls and boys, to map out like their growth trajectories. Ideally, we would take then that cohort and track them over time. So then not only do we have like a cross-sectional, but then we have a kind of longitudinal progression, but which is definitely feasible, just kind of something to, yeah. Okay, that was just that. So with that, I'll kind of acknowledge our partners. Obviously, this has been an exciting partnership with a number of different individuals that I'm kind of listing here, but and really thankful to our funding organizations and all the Springbok team.
I have a question about clinical trials. So you are at least an endpoint for some clinical trials that are ongoing right now, correct? This digital twin sort of model is being used already for adults, is that correct?
Correct. Yeah.
And they're matching it with function as well, right?
Yes. Yeah.
And
Yeah, I mean, they're focused mainly on the muscle level data as an output for now, because that's kind of like the most kind of similar. I think all the trials are still kind of trying to figure out what functions they want to use. So, which I think, we really, hopefully with these ongoing studies, the MOVE and the Move Peds will help really clarify that. So not everybody's not doing like a different thing or kind of reinventing the wheel there, but yeah.
I mean, the other piece of it too is that, as Sylvia mentioned in one of those slides or referenced, is that so we have all of the fulcrum data from their phase 2 and phase 3, and so we're um, talking with a lot of different, whether it's the drug development companies or the innovation hub or whatever about that's wildly valuable data that we could, and we're free to use it and analyze it, along with all the other metrics that they and patient variables that they gathered. So, um, you know, the goal is to analyze all that data, build out the data lake. Obviously, that's adult patients, but it's going to inform everything. And either we're working with, or you know we're deep into discussions with pretty much every company that's developing drugs in this space. So we're with the Epic Bio trial. There's others that we're under NDAs, but we're, other than one or two, we're really going to work with or are working with those other ones. And we were really thoughtful as well about kind of building into all of our contracts the ability to not only analyze their data, but to be able to feed it into the data lake.
Good. I think just, you've mentioned this several times, it's just we don't have any data on kids and we don't have any data on non-ambulatory adults because none of them have ever been studied. They've never taken MRI on any of them, so we're kind of behind the power curve on a lot of that stuff. And just the data you were showing shows that they're not the same, like the way kids develop. And so I think Move Peds Plus is good, but it's 2 years, and just looking at your data, how much function are kids going to lose in 2 years? We obviously sooner, we want treatments and trials to go into kids sooner rather than later. But I think we're just kind of playing catch up now.
Yeah, totally. Yeah, it's a good way to yeah, I mean, I think, it's exciting that these treatments are coming online. I think in some ways, which is, this is like, I don't know, catch 22 or something, but like the treatments have come online, but like they're almost ahead of the understanding of the disease in some ways. So I think that's what we're really trying to accelerate, to the understanding, so that we're understand it enough to figure out if the drugs are working, because it's challenging.
Right. Well, I think you guys are doing great work. We just need to get the data on the kids, and we need to get that normative data as well. We need to start working on that. 100 kids is a lot, but we need to at least get some, I guess, huh?
Absolutely.
Somewhere.
Yeah, I mean, it's actually feasible. The setup that we have at UVA is certainly something that we, it is in many ways that typically developing children are easier to recruit than like aging adults because I don't know, they're easier to access through communities and everything. So yeah.
Well, it's exciting stuff. I think, there's 1,000 different ways you can go with it. There's 1,000 different things you can study, and the more you study, the more questions, right, you have about
Yeah.
why this is happening to a certain muscle and not another muscle. Because the hamstring thing was particularly interesting to me because the doctor said, "Oh, Sam's hamstring muscles, I'm sure they're shot." I'm like, "No, his hamstring, they're fine. It's his quads." And they're like, "That's not right. That's not typical." And I'm like,
Right.
well, for a kid, it is." I just saw it.
Absolutely.
So
Yeah, we have the data. You can send this to your.
I will. I'll be like, "Look, see."
Yeah,
But that's just strange to me that's how it, it doesn't make sense.
yeah.
There's no reason why that should happen, but I guess it does. We don't
Yeah.
know it yet, I guess, huh?
Yeah.
Well, thank you for your time and thank you for the presentation. I think it was really interesting and very informative. And I think we have some things to work on, and hopefully we can help you help us. So
Absolutely.
keep in
Yeah.
touch. You know, we're certainly interested in the pediatric population, and then those that grew up with the disease and now are, you know, half of them or more in wheelchairs, and they're also on the outside of that
They are.
treatment path as well. You know, it's not ethical in my mind to let the kids deteriorate to a point that now they're in chairs and now, oh, we can't help you because you're in a chair. Because I think if you looked at your data, and I don't know how much data you have on non-ambulatory adults, they have a lot of muscle still to lose, right? And it's frustrating to hear like, oh, they're, you know, they have the floor effect. Yeah, I guess if you have one of your chunky whatever things you're using, but an MRI will show that they have a lot of muscle to lose.
Absolutely.
And so
You're
they
right.
have a lot of muscle left to preserve, and we need to make sure that they
Yeah.
get on that
I
path
think
to
it's
treatment as
more
well.
important because they're really relying on those muscles to do everything.
Right,
Really.
right. Well, thank you so much. Does anybody else have any questions? I think we're at time. I appreciate you coming on and giving us this presentation. And if I get any questions, I'll shoot them to you. I have your email, and if we get any in-depth questions that I certainly can't answer, I'll forward them to you. But thank you so much.
Yeah, thanks for
You
having
guys
us.
have always been very generous with your time and talking to me, and I appreciate that very much.
Thanks for the invitation. We're pleased to
Thank you.
Good night, everybody.
get it.
Night.